Okay, so let's finish the business. So the last part is on some of the methods that people use to make that all work in high dimensions. It's not a complete thing. It's just some of the techniques that are important. And I want to begin with to give you a simple, well, relatively simple mathematical argument why you can't just do filtering in high dimensions, why it doesn't work with the techniques that people came up in the 80s and 90s in Monte Carlo techniques, which all rely in a way on the idea of importance sampling, where you approximate the quantity you want by a weighted sample, and the weights are the importance weights. So they basically measure how well the forecast agrees with an observation. So, and remember that earlier this morning I talked about effective sample sizes, importance sampling, in the first part of my lecture. That was the quantity that related the sample size you have to the real sample size that you can count on in a statistical sense. And there was this factor rho, which is smaller than 1. Ideally, it should be 1, but basically, as soon as you have non-uniform weights, it's more than 1. And now we're just going to look at the thing, how it scales in dimension. And so there's this estimate on rho connecting it to this Kullback-Leibler divergence that was a measure of distance. And take the idealized setting where you have a dynamical system that each component of a large dimensional system is actually doing its own thing. Like take 10 copies or 100 copies of the Lorentz 63 system, which is 3-dimensional, and just stack them on top of each other to get a high-dimensional system. Or take the Lorentz 96 system, which I guess wasn't part of the hands-on session, but you did the Lorentz 63 system. So just think of some system that's just doing identical things in each component. And so basically then the probabilities are each independent for it. So you have a product of probabilities. And then Kullback-Leibler takes the log of this. So if you have a product that becomes a sum, so you basically, the divergence, this Kullback-Leibler divergence, then sums up. So you basically get the Kullback-Leibler divergence for one single Lorentz 63 system, but then 100 times. So you times 100. And so this gives you a feeling why this scales exponentially in the dimension, right? Because Kullback-Leibler has this property: if things are independent, then it just gives you a sum of identical things for each independent copy of what you have, right? That's of course a worst case scenario, but basically it goes exponentially down in dimension. And so to compensate this, you have to increase the number of particles exponentially, and you're dead pretty quickly, right? And of course, that was one of the reasons why in the 80s and 90s and late, I mean, nobody thought that you can ever make particle filters really work in high dimensions. Okay, so what are remedies for this curse of dimensionality, which actually also applies to Ensemble-Kalman filter? Not quite in the same severe way, but you cannot apply the Ensemble-Kalman filter, as I told you earlier, and also how you did it in the hand-on session, to such a high-dimensional problem. It would still give you difficulties. So, well, there's variational data assimilation. It's one technique, but the important thing is really localization, ensemble inflation. And then I want to talk about two other things that, I mean, localization and ensemble inflation, these are operationally used. And the other two things I will mention is sort of ongoing research work that various groups do. So I will at least point you to some of this, what are the ideas that are being followed in the research. Okay, so 40WAR, I mean, that you had in the hands-on session, so you write down this cost functional. and you can minimize it. Now I write it here a little bit in a maybe unusual way. So remember that I assume there are model errors. So this is what the model on its own gives you, but I don't request anymore that it goes to 0. And there's a penalty term for this. So in your 4D var implementation, that penalty didn't exist because you assumed your model is exact. So I'm talking here about the weak form of 4D var. So this is one penalty. Another penalty comes through the observations, and that measures the mismatch between what you forecasting in that variable and what you actually observe. And then there's a cost. I mean, there's a penalty for the prior. All right, and then you can minimize that, and you can also try to there are techniques to approximate the second order information. If you use a Newton method, a quasi-Newton method, that gives you sort of for free some sort of approximation of the Hessian as well. So you actually don't have to explicitly compute it, and that's a fairly robust method, except that you have this minimization problem that you might get stuck in local minima, and you have to compute gradients. Now there's one technique that also another technique that's was invented in a different field in oil reservoir exploration, and is heavily used there, where they said, well, we not just want to know about the minimum, we like to get some information on the uncertainty as well. So we want to have actually some sort of ensemble type of thing. We want to sample, we want to have some sort of samples from the posterior distribution. And that's a technique you can apply straight to your 4D var system. And the trick is extremely simple. You basically perturb all the quantities, you add a random perturbation to all the things. So for example, you have the background state, x bar, right? So that was x is the thing you want to estimate. That was the background state. Now you perturb that by a random number distributed according to your uncertainty in the initial condition. So P naught is a covariance matrix in the initial condition. The same you do with, you formally add or subtract, doesn't matter, the Gaussian variable. You add an artificial model error term. You choose a random number from that distribution. So Q is the model error. And you do the same. You perturb, in a way, you add an error to the measurements as well. So it's a bit like this perturbed ops ENKF. Except you do this in this cost functional. So you plug it everywhere in. And then, again, you minimize. And now each time, because you get a different minimizer, because you added sort of random quantities into it. So if you set them all equal to 0, you get your standard 4D var. If you add them, you get sort of other quantities. And so you get a cloud of points suddenly. And of course, you can ask yourself, what is this cloud of points now representing? Now, one thing we know about it is if everything is linear, then you're basically back to the ensemble Kalman filter, and statistically it's all correct. That's good to know. In the nonlinear case, it's still essentially an open question. I mean, what exactly is sampling from? The experience says it works quite well, and in many cases it does. But it's clear that you're not sampling from the exact distribution. Actually, you can write down this distribution that you sample from, but it's a horrendous expression. It involves Jacobians, so you need the second derivative of this and the determinant of it and the determinant of it. So it's not something nice. So in principle, yes, as a mathematician you could write it down, but you can't really implement it to use this as a proposal step in a precise way. But anyway, it's a method that's it's very popular in oil reservoir explorations and in history matching, and it is popular because it allows you to use known technology. I mean, if you have a 4D var system, you can use this. Right, so if you stick to this sequential approach, you want to do the E and KF in high dimensions, then you have to do localization. Now, localization is a very intuitive idea. So far, I denoted states by X. Now, this notation is a bit unfortunate because X is also I mean, we're now talking about fields with a spatial domain. And so normally we denote the domain by X, the position in the domain. And so X is now the spatial location, T is time, and U is now the quantity, like a velocity field or vorticity field or whatever you're trying to estimate. So now you're really talking, you're trying to estimate functions, right? Of course, you have a grid, so ultimately it boils down to gridded values you try to estimate. But in a way, it's and so also your prior is actually now a Gaussian process, strictly speaking, if you go to the limit. And we're back to the very beginning this morning where I said, well, if we go to the infinite limit, so you're really trying to estimate functions, you're targeting Gaussian processes, and there are these subtleties that they're not mutually continuous, right, like in finite dimensions. Anyway. And so let's say you observe that field at a particular point. That's to be like temperature. Let's say U is temperature, and you measure the temperature in this room, and that's one location, X, right? And then what the standard filter is doing, you're computing, again, these coefficients, Dij. And these are just, is an M cross M matrix. And you apply it to all the locations, to all the X's in your domain, right? So you would, I mean, we did this here in Kobe, but you would apply the same coefficients in Berlin. Right? And that doesn't seem quite right? Because that I measure the temperature in here and that I change the fields in here shouldn't really matter so much in Berlin. And so there are these localization concepts where basically the idea is that there's a decay of correlation spatially, and so you should just adjust these things locally, and the way you do this is by making these coefficients space dependent, and the LETKF was the first to do this, as far as I know. But you can all the filters I talked earlier. I mean, these particle filters you can now localize. And the second order filters where you do the second order approximation at the end, you can also apply the same kind of localization idea that because they all fit into the same framework. So all these filters are now localizable. So you do local updates, and so that breaks or helps to break the curse of dimensionality. So our localization works the way that you artificially, in a way, increase the measurement errors so that observations that are far away are not taken into account when you compute these coefficients at a particular location. I mean, that's the essential idea without going in all the really needy details. Right. So this is about localization. Inflation is, I mean, if you talk about multiplicative inflation, so that you increase the spread in your ensemble by this linear scaling here. Now, again, if you think about this incrementally, there's an interesting dynamic interpretation which leads to sort of mimicking some sort of model error. And basically, if you look at this, this looks a bit like an Euler step of this SDE with a step size alpha. Right? So this is this. Now, viewed from that point of view, it's again sort of an ODE that interacts. So the particles interact through the mean because they see the common mean. So we're back to interacting particle systems. And that you can show statistically, if you have a large number of particles, is equivalent to Brownian motion, right? These zigzag curves, not pathwise, but in terms of the marginals, and we're interested in marginal distributions, right? But the pre-multiplying matrix, the diffusion, the Q, which I had before, so the model error was a covariance a matrix Q times Brownian motion. That was the standard error model we use in SDEs. Now it's the covariance matrix itself. So this is a funny way of modeling. So it's you use sort of the forecast uncertainty itself to decide about the model error in a way, if you go this interpretation. And again, in Brownian motion, you replace this by a constant matrix. In fact, there's this analogy of Brownian motion. So basically, if you want to mimic Brownian motion as an interacting particle system, you can do this by eliminating the noise completely and replacing the noise, the Brownian motion, by this kind of interacting particle representation where there would be a Q here and a P inverse. That's the equivalent of the interacting particle representation of the model error being Brownian motion, right? So again, there's this correspondence between Brownian motion and having certain interactions between the particles. And it's repulsive, which gets me back to this sort of game theoretic interpretation of data assimilation, that basically model errors have the effect that all the particles separate because Brownian motion adds something that drives them away from each other. It's not exponential, right? It's not like a true instability of a dynamical system where a Lyapunov exponent or something goes, or just a linear setting, you have a positive mode somewhere. But it's sort of sub-exponential, and Brownian motion is sort of on average a linear increase. So it's a weak form of instability, right? And of course, I think that's actually one thing. At least I like to explore further in S4. If you have ensembles anyway, you can use this to model model errors or represent model errors without actually going stochastic. Because that's something, for whatever reason, some people don't like so much.